Hi everyone, welcome back to the course on biosensors and lab-on-a-chip microsystems. I'm Dr. Hadar Ben-Yoav from the Ben-Gurion University of the Negev in Israel. And today we are going into lecture number 4. We're actually arriving to the middle of the course. And the middle of the course that we are going to focus directly on molecular level reactions that happens at the surface of the interface of our transducer. Split video from slides. No. Okay. So far, we had 3 lectures about a system level, about how the system looks like. We learned about, something new for me. About the system level, both are lab-on-a-chip microsystems, how you can integrate multiple components, multiple parts that have different functionality. You have to remember that a lab-on-a-chip is a microsystems of multiple parts, while each part had its own functionality, such as separation or detection or mixing. And all of that is being integrated with microfluidics network. We also learn about how you actually can use microfluidics for as a functional part, such as filtering, separation. And today we are going to learn how what happens, what kind of physicochemical processes happening at the molecular level at the interface of our transducer, and how we can actually model it. So the goal of this talk will be today, the lecture, is to recognize different types of receptors, and we will remind ourselves what are receptors soon. And then we are going to try and analyze different mechanisms where the receptor interacts with our analyte. What is a receptor? So far you have seen this kind of scheme multiple times. And these are the 3 components, remember 3, not 4, components of the biosensor, of the sensor part. It is based on, usually look at there's a receptor, a part that gives a selectivity to the sensor. There is this chemical transducer, which its goal is to transform the binding or recognition event from the receptor and the analyte into another type of a signal that later on can be measured as the output signal. And these are the 3 parts of the sensor, and we have the analyte. The analyte is the actual marker, biomarker or marker or molecule that is related to the disease, and it could be either protein or DNA or any kind of biological molecule, biochemical molecule that is related to the disease. And the best thing is that it's going to be as much as relevant to the disease and not to other type of disease reactions, other diseases in the body. So the receptor goal is to provide the capability to recognize the analyte. And here you can see kind of like how it fits kind of the structure, but it's only for the scheme purposes. But eventually, if it won't be selective to the analyte, then we won't get any signal that is related to the actual analyte that we have. Any questions on this slide? Okay. Now, which type of receptor do you know? What types of receptors? So receptors that provide the selectivity could be either biological in nature, such as antibodies or enzymes, could be chemical, such as synthesized molecule that provide the electrocatalytic activity. They can be also either type of selective or semi-selective. Now there is the range of selectivity, while on one part you have non-selective, which basically you will detect any type of molecule without any selectivity. And on the other part range, there is the specific. So it means it only will bind to the specific analyte and not to other molecules. But it's never like that, it's never 0 or 1. There is always some type of selectivity in this kind of range. So we would like to have that kind of receptors that are more selective towards specific molecules, but there are also semi-selective receptors that are selective to a bunch of molecules, such as a group of molecules. For example, we have enzymes that are semi-selective. Okay, they can provide reactions to different types of substrates. Therefore, they are semi-selective, but to a group of molecules. Do you know any other types of receptors? Any ideas? Does anyone have any idea or example of another receptor? Some kind of component that provide the selectivity. No? So for example, cells, biological cells can be type of receptors. What does it mean? That this kind of cell, biological cell, can be integrated on our sensor, that whenever it feels like a white blood cell, it feels some kind of presence of a pathogen, it will respond. So therefore, it provides a selectivity, selective response of the sensor, that whenever we have kind of a pathogen, it will react. And if we don't have the pathogen, then it won't react. Okay, any questions on this slide? Now, what happens at the receptor-analyte interface? And we are talking now on the receptor-analyte, that's what we're going to focus, the analyte and the receptor part. So there are different types of processes, chemical, physical processes, such as mass transfer. We discussed about it yesterday, about how fast, for example, the analyte transfers to the surface of the sensor, and then there's some kind of receptor-analyte binding reaction. The receptor and the analyte, they bind, disconnect, associate, dissociate all the time. Biocatalysis reactions, enzymatic reactions. So all of those are kinetic reactions that has different different effect on eventually on the whole process of the analyte coming to the surface of the transducer and being detected. Now, when we look at a system and we analyze a system or lab on a chip, we look at what are the building blocks or what are the processes that we have during the reaction. So for example, we have an analyte diffusing toward the surface of the transducer, and then there is the binding. Okay, so we have two processes, diffusion or mass transfer and receptor-analyte binding. Now, after we analyze the different processes that are going through the lab on a chip, then we need to identify what is the limiting or the limiting rate reaction that basically defines the overall reaction rate. So for example, if we look at this kind of scheme of different funnels, and we pour the same amount of water, but we have a small funnel here and two big ones. So the rate that the bottle will fill with water will be dependent on the rate that the water goes out from this funnel and not from the other ones. Okay, makes sense? This one going very kind of slower than these rates. When you look at the other example, that the smallest one, which had the smallest diameter, is in the middle, so it doesn't matter, again, how fast we're going to flow the water from here. Eventually, this rate, the rate that the water flows from this funnel, will define the rate that the water will fill the bottle. And also for the third one. So basically, what we see is that the one that has the reaction, so if you can kind of like compare it to different mechanisms such as mass transfer, and then receptor analyte binding, and so forth. So the reaction that has the slowest rate will define the overall detection rate of the sensor. So it doesn't matter if you look, this one is diffusion, and this one is receptor analyte binding, and the diffusion rate takes place, and it's slower than the receptor analyte binding. So it means that molecules take some time to diffuse towards the sensor, towards the transducer, and then whenever they get into the receptor, they bind very fast. So it doesn't matter how fast the binding is. It matters how fast the molecule diffuses to the receptor. And we have to remember that this reaction, the slowest reaction, the one that limits or defines the overall reaction rate. Okay, do we have any questions on that? It's an important slide. Okay. Oops, other way around. Now, how do we model the bio-interface? And for that, we want to change it a bit. Okay, it's nice. So with that, we look at a specific example, okay? And again, we can model, and eventually we want to come up with a series of equations to describe the behavior of for example, what happens at the interface, of the biological interface, such as we looked yesterday about the equations, the Navier-Stokes equation, and so forth, to describe the flow in the channel. So we have an analyte ligand binding. Okay, this is kind of the example that I'm looking at, and the analyte ligand is a type of basically the receptor itself. It bound to the detector, to the transducer, and the analyte diffuse, and then whenever it comes near the receptor, it binds, it associates and dissociates, meaning it's binding, but it's never, it's never 0 or 1 in biology. It's where the most reaction happens. So the analyte binds, but there are some portion of several analytes that dissociate, that's being removed or doesn't bound eventually to the receptor. So there are two reactions. That's why we have kind of like let's say in equilibrium or in equilibrium reaction. And what we look here, the response of the detector, meaning that whenever the analyte binds to the receptor, we get a response, some kind of a signal. So this is the y-axis, and the x-axis is the time. And at the beginning of the time, we have a baseline, meaning that we have this kind of receptor. I mean, this is the ligand. It's a kind of like an antibody. And all the antibodies are bound to the surface. They are not connected to any analyte. Okay, so we have some kind of response because always you have some, it's not, you don't have zero response, you always have some background response, but it's constant because there's no binding. At time here, we introduce to the system the analyte, this kind of rounded white black balls. And then over time, we have more and more analyte bound to the antibody, the receptor. So the signal increases because more and more analyte binds to the receptor. Now, at some point, sometime after some time, all the antibodies, all the receptors bound to the analyte. So we don't have, it doesn't matter if we have more analyte, still we don't get more binding effects because all the free areas, all the free locations of the receptor are occupied. Here's what happens here, and therefore the signal stays the same because the number of the receptor bind to the analyte are the same, is the same. At some point, we are removing the solution, the sample itself, all the analytes. So what happens? Due to thermodynamic considerations, now the analyte dissociates from the receptor. So the signal decreases over time because the more time, the longer time we have, less and less analyte are bound to the receptor itself. That's why the signal decreases. Any questions on this kind of scheme? It's clear you have association, dissociation, and equilibrium in the median. Does anyone have any question? No. Okay. If yes, please ask. It's okay. So now let's try to explain it. And we look at reaction kinetics. And reaction kinetics, let's try to describe each one of the stages. Yes, we have the association, equilibrium, and dissociation. So for the association, if we describe L as the ligand or receptor concentration, A is the analyte concentration, and LA, which is also R, it's the receptor analyte complex concentration, meaning this one, generate signal. So the rate, it changes when we have the association part. We have Ka. Ka is association rate constant times the concentration of the ligand and the analyte alone, because this is the rate that we have the generation of the LA, the complex, minus Kd, which is the dissociation rate constant, times the complex. Because remember that although there is binding, there is some complexes that dissociates back. So that's why we have a minus, and we have the KdLA. So this is the reaction kinetics we described for dissociation. Now, what happens when in the dissociation, and sorry for the different letters, LA is now R, the bound complex, and the change in the bound complex, it's become decreasing again, and we look in the R and LA because they provide the response. They describe the amount of this antibody or receptor bound to the analyte. So the rate it changes is minus because dissociates. It goes and decreases. Kd is the dissociation rate constant times the amount or the concentrations of the complex itself. Okay, so far it's kind of straightforward reaction equations, rate load. Now, when we look at the steady state, it's meaning that we have a lot of analyte, but we get into the R max, which is the maximum amount of receptor bound to the analyte. Sorry, any questions? No? Okay. So it means that it doesn't change. And what happens is that if we solve that, which is actually 0, because it doesn't change, right? So it's 0, we get the description of LA, which is our equilibrium equals C, is the concentration of the analyte, times R max. R max is the total concentration or the maximum concentration of ligand and receptor. Sorry, receptor and analyte complex bounded, divided by C plus KD. And KD is the concentration, is the ratio between the dissociation and the association rates. Okay, so any questions so far on this slide? Like this? Okay, any questions? Please ask, it's important that you understand this. Okay. So let's take an example of antibody antigen. Okay, and for that, I want to share something else. And it is, second, oh. You see the paper? Yeah. You see? Okay. The example is that we have some kind of system that has antibodies, like the one you saw before, and analytes. Now, there are 3 types of materials, or 3 types of biomaterials here, or phases. We have the free analyte that is not bound to the receptor. We have the free receptor that is not bound to analyte. And there is the receptor analyte bound complex. Okay, so we have 3: the analyte, the receptor alone, and the complex of the analyte receptor. So we would like to know what is AR. Remember, the complex tells us the signal itself, because whenever it's bounded, we have the signal. So the reaction, the equation rate, the reaction equation is that we have a free analyte plus free receptor. K1 is association into the bound analyte, and there's K minus 1, which is K dissociation back to free analyte and free receptor. So in equilibrium, and if you remember, we said sorry, a second. Do you see me writing? Do you see the writing?
Yes.
Okay. Thank you. So if you remember, we said that DAR divided by the no, it doesn't work. It doesn't work. It's weird. So what we're going to do is use this one. So we said the DAR 2 dt in the association. We have K1, right, times A times R minus K minus 1 AR, concentration of the complex. This is the equation we saw in the previous slide about the reaction kinetics of the association. So in equilibrium, this one equals 0 because it doesn't change, right? Therefore, this part will go to the other side and we get this equation. Okay, this is the origin of this equation. K1 AR equals K minus 1 AR complex. Okay? And now we look at the affinity constant. The affinity constant, again, is we said the K is the K itself, which is the ratio between the association and dissociation. And therefore, K1 over K minus 1 equals AR over AR, A times R. And now we look, third thing we define that AR, the concentration of the complex plus the concentration of the analyte, means how much total analyte we have is C, right? Because some of it connected to the receptor, some of it connected to the analyte. And the total amount of receptor that we have is R0, meaning that we have those that is free and the one is bound. Now, let's take this equation, K equals AR over A times R, and we're going to replace the amount of concentration of analyte to C minus AR. Okay, so this A, so basically we move this one here and we get minus AR and that's how we got this one. Same thing for the R0. Okay, we click the R0 minus AR. And we do some kind of changes, multiply by this, and we get K times C minus AR, the complex, times R0 minus AR, the complex, equals AR, the complex. Now let's see what we're doing with that. And remember, we want to know what AR equals to. So we're going to differentiate, or we get the AR from one side and we see how it looks like. And for that, let's take two different types of cases. One, that we have very high analyte concentrations. So the analyte is concentration of the analyte. This one is very, very, very high. Okay, so this one is very, very high. We don't have the limiting molecule is the amount of receptor that we have. Doesn't matter how much analyte we have, we always have analyte that binds to the receptor, but we don't always have a free receptor that could bind an analyte. What happens here is C is much, much, much bigger than the complex AR. So C is much, much bigger than the complex AR, meaning that we can do K times C times this one. We can neglect this one. This is what we see. KC, this part equals AR. And we get KCR0 equals this part, and we take AR on one side, and we divide this part by the 1 plus KC, and we get this equation, or we also normalize it by R0 because we want to normalize how much signal per receptor we have. And we also, what we get is 1 over 1 plus K minus 1 over C. Now let's see what happens in a very low concentration, in very high analyte concentrations. So what happens is that the normalized signal, this one as a function of the concentration, looks like this kind of curve. When in a very high concentration, the analyte doesn't change anymore, and we get into the normalized of a stationary maximized value of 1, meaning that the amount of AR doesn't change. So if we have high concentration of analyte, we're going to see this kind of the signal that is dependent on the concentration and looks as dependent as this kind of equation with C. Okay, so questions so far? Okay. Now, in most cases, when you use a sensor, you don't have a lot of the analyte. Usually you want to have a sensor that is very sensitive to low concentrations of the analyte. So let's take the B option, that when we have a very low analyte concentration, which means that the analyte is the limiting factor. So what we get is that R much bigger than AR, meaning that you have a lot of free receptors than those that are bound, because don't have a lot of analyte. And then when R is much bigger than AR, R is almost like R0. Okay? And then we put it in this equation. And you get KC minus AR times R0 equals this AR, and KCR0 equals AR and 1 plus KR0. And we can, again, we get AR over R0 to get our signal equals KC over 1 plus KR0. This is our normalized signal. And this kind of equations tell us only if we have very low concentrations of analyte. It's different than this equation. This equation told us for the high concentration analyte, and this equation, it's different than for low concentrations of analyte. So if we look how AR over R0 changes the function of C, we identify that this is kind of like a linear relationship, where this is the constant, meaning is that the more concentrations you have, more concentration of analyte you have in a low concentration of analyte, you increase the concentrations, the normalized signal will increase accordingly in a linear relationship. And the slope, which is the constant here, is K over 1 plus KR0. And see what happens now. K, it's K1 over K minus 1. So basically, we cannot affect K or K minus 1. Now, if we want to get a much sensitive sensor, because the sensitivity is the slope. If we have a slope like this, it means that any change in the concentration, small concentration change, will cause a much increase with the signal compared to a sensor that have this kind of slope, that is less sensitive. So this, we want to have the slope as bigger as possible. So in order to increase, to make it much bigger as possible, we need to have our zero as slower as possible. Meaning that if we have our zero very, very small, this whole value, this whole fraction will be very, very high, and the slope will be very high, and we get high sensitivity, meaning that we actually can control if R0 is the amount of the receptor on the sensor. If we increase the concentrations of the receptors on our sensor, we can actually increase the sensitivity. See how cool it is? I mean, we just described in equations the reaction kinetics of analyte and receptor interactions. And we got this equation that tells us that if we decrease the amount of the receptor, remember this kind of receptor, we want it to have as small as possible, we actually increase the sensitivity of the sensor in a low analyte concentrations. So if we look again what we have done, we wanted to describe the system of analyte plus receptor going into analyte receptor bounded, and we wanted to see how the signal AR depended on the concentration of the analyte. So we solved it in equilibrium, and we looked at two special cases for high analyte concentration. We get this kind of dependence, the concentration. For low analyte concentrations, we get this kind of linear relationship. And we said that if the slope is the sensitivity of the sensor in a low analyte concentrations, we can actually decrease the concentration of the receptor that will increase the slope and increase the sensitivity. Okay, any questions so far? Okay. Oh no. Okay. Where are we? Oops. Okay. So I also put added that into the slides, so you have it at home also. And now, and I guess today we're going to have a bit shorter class. We're going to finish in about 12. So the idea here is let's look at the sensor and analyze the binding reaction, what happens, and the bio interface of the sensor. So this paper was published in 2007, and it's published in Microscopy and Microanalysis, an antibody by Nojiva. An antibody synthesized microfabricated cantilever for the growth detection of Aspergillus niger spores. Aspergillus niger, it's a kind of a mushroom, okay? It has some spores, basically single cells of the mushroom before it starts to be infectious. And this guy developed a sensor that has an antibody that binds to the spore. So so the antibody is the receptor of the sensor, right? Because it provides the sensitivity, the selectivity. And the transducer is the cantilever. So it's kind of like a cantilever that resonates. And because it's and you're gonna see that it's the resonance frequency is dependent on how much spores being bound to the surface. This is how it looks like. Very cool. No. Okay. What is the goal of the paper? Again, I always start with the motivation. okay, why even bother and develop this kind of sensor other than it's kind of cool, but we need to have a real world scenario, real world need. So it's written here, and the idea is to detect, it's written here, fungal, yes, or not mushroom, fungal spores of Aspergillus niger because it causes infections. And the idea here is to actually detect the growth of the spores. So spores of fungus are actually dormant. It's fungus which is kind of sleeping, is not growing, it's not infectious. And in order to be infectious, the spores needs to grow and to grow into many fungus, and then it will be more infectious. So the idea is to see or to do the sensor that will measure whenever we have the spores, they will start to replicate and to grow, and we're gonna see some signal with the detector itself. Now, yes. What are the components of the lab on chip? What is the analyte? So first, we look always at the extracted signal, and here it's the output signal is the resonance. So the idea is that you have a cantilever, it resonates at specific frequency. Now at some point, at some point it actually resonates in the maximum amplitude. Okay, so you increase the frequency, and then it resonates with the maximum amplitude, and then you increase the frequency, and then it decreases again. So this resonance, there's a specific frequency that is dependent on the mass of the cantilever. Now the idea is to put some antibodies here, that whenever the spores will be present and will bind to the antibody, it will change the mass on the cantilever, and this frequency, when it gets into the maximum frequency, this one will change. Okay, we're gonna get it in a different frequency because of the difference of the mass, and I will show you how it's related soon. Now we have a laser. I mean, how do we know that these cantilevers, they resonate, or what is the frequency? We shoot laser on the surface of the resonance that reflects into a detector, photosensitive detector that has many pixels. And what it measures is that, this is the point of the laser. When the cantilever is in different location, it will affect the point. So the point will move. This is how it measures to see the maximum frequency that the cantilever can get. So the output signal is the frequency, the resonance frequency. The receptor is the antibody, right? It provides selectivity to the spores. And the transducer is the cantilever itself. It translates the binding of the spores to the antibody into resonance mechanical. It's a mechanical transducer into mechanical signal. What is the analyte? It's the spores itself, what binds to the receptor. And how does it look like? If this is the surface of our cantilever, it was functionalized with some chemicals reactions. It doesn't really matter what kind of material, but such as aptes. Aptes, first, you introduce the substrate because it's made of silicon into aptes. So silicon oxide bind to the silicon side of the aptes. Then we get like a silicon, and we get an amine group at the end. Then we introduce glutaraldehyde, which bind to the amine group and provide free oxygen or aldehyde part that now we can use this kind of protein A that you bind to that, and on top of it bind the antibody. So it's a kind of a process steps that you make to build your receptor, to bind the antibody through this protein and some serious glutaraldehyde naphtase to the surface of the cantilever. Now, when we introduce the spore, it will bind to the antibody. And the antibody is very specific to the spores, meaning that if we don't have spores or we have other type of fungus, they will not bind to the antibody. Only this kind of Aspergillus niger spore will bind to these antibodies. So again, how do we recognize the receptor? We look at what could be missing here that could prevent from detecting the Aspergillus spore, and this is basically the antibody itself. If we don't have the antibody and we have everything in the protein, the spore will not bind specifically to the protein. We need the antibody for that, so the antibody is the receptor. Any questions on this slide? Okay. What is the goal of the experiment? Now, I promised you the theory of cantilever frequency, resonance frequency, and it's dependent on the mass. And this is the equation that correlates the mass, the total cantilever mass that we have equals to the cantilever spring constant. It behaves like a spring over 4 pi squared times 1 over the resonance frequency squared. What does it mean? That the higher the mass of the cantilever, the smallest the resonance frequency. So it actually gets into the maximum frequency, the resonance frequency when you apply lower frequencies. And if the mass is very, very low, so very small changes with the amount of spores that bind. So this is very low. The frequency will be very high. So a lot of changes we put some small mass, the change with the frequency won't be very much bigger, won't be very changed. It won't be very big. So, yeah. So let's see what happens. And the amplitude tells us the intensity of the resonance. And here we apply different frequencies. Okay, we apply different frequencies. At the beginning, we apply 26 kilohertz, and then gradually we increase to 27, 27.5 until we get the maximum amplitude. And we see that we have A, B, and C, and the maximum amplitude get in those 3 different frequencies. So let's see what this means. So we have the amplitude. The amplitude is a function of the frequency that applied, and the resonance frequency is the one where you have the maximum. So A is the initial frequency of a cantilever without anything, just the cantilever, no spores, no antibody, nothing. And we can see that it has the resonance frequency F1. So it's about what is like 27.1, something like this. Now, B is when we actually introduce the antibody itself. Now, we put the cantilever, we add the antibodies, and we get some spores bound to it at the beginning. And it looks like this. Spores dormant, they are sleeping, they don't grow. So we get some change with the resonance frequency. The frequency actually changed. The resonance frequency now is 26.8. Before it was 27.1. So actually the resonance frequency decreased. And it's very much related to what we saw here because now we have more mass. So the frequency, resonance frequency will decrease. Actually, it's easier to look at it like that. Okay. So if we divide and see that actually, yeah, so the more mass we have now, because you have the antibody and some spores, the frequency, resonance frequency decreases, okay? Because you need this value to increase. So what we see that indeed the frequency decreased. Now C is when the spores, they start to grow. They wake up, the fungi start to grow, they multiply, they become infectious. This is the image of, you see a lot of spores, they bind to each other. On top of it, cause such a biofilm of fungus. Now we have more and more mass now. So the frequency will decrease more. The resonance frequency, remember, this is the resonance, this is the frequency where we get the resonance. So C, the frequency is even lower. So again, so this is just a bare cantilever, the highest frequency resonance frequency. Here we have some spores bound to the cantilever. They are dormant, they are not growing. And see, they're already growing, they wake up and start growing and get more and more mass, therefore the frequency decreases. Any questions on this slide? Okay. Now, in this experiment, they said, okay, so we see that we get some changes with the frequency. Let's now look at it and leave the spores to grow and see what happens to the resonance frequency. And this is Y. Y-axis is the resonant frequency, which is F. And this is time over hours. Usually it takes about overnight, like about 18 hours for the fungus to grow. So the first experiment is the control experiment, it's the reference cantilever. It's a cantilever with the antibody, but no spores. Okay, only antibody. And you can see that over time, the resonance frequency stays the same. It stays the same because it makes sense because the mass doesn't change. We don't have any spores there, it's only the antibody. Now, when we introduce, when you have a cantilever that introduce spores, this is the rectangle ones, the square ones. What we see is that over time, the frequency starts to decrease until it gets into a steady state. Now, frequency decreases, meaning that the mass increases. Remember, it's kind of like tricky. Frequency decreases, meaning that the mass increasing. So that's because the first stage, we have it's in 1, 2, 3, 4. There are 4 different stages of the growth of the spores. The first phase, okay, is the lag phase. Lag phase means that we put the spores, we put them some nutrients, and it takes for them to time like to wake up and to start catalyzing the nutrients to start growing. So this is the lag phase. Number 2 is the exponential or the log phase when they start to multiply exponentially. The third part is the deceleration. So they become the multiplication rate decreases because Could be many reasons, such as usually it's because they don't have enough nutrients for everyone. They kind of finish the nutrients, and not all the spores have enough nutrients for them, so they decrease the growth. And the fourth part is the stationary part, which meaning that now they don't have enough food, so they just stay the same concentration. So very nicely, these guys, they develop a sensor that can detect spores only by the change of the frequency or by the mechanical change of the cantilever. And they actually can continuously measure, continuously monitor. It's kind of semi-continuously, but meaning that putting the spores and the nutrients in the cantilever and then leave it like this and measure every half an hour. So they could use the same sensor repeatedly and measuring the resonance or the amount of spores for different time periods. Any questions on this slide? Okay. Now, what could be the problems of this lab-on-a chip? What do you think? Why do you think this kind of device, what are the problems to have this kind of sensor in order to be used for spores detection in the air? What do you think? Any ideas? Anyone? Don't be shy. By the end of the class of the course, someone will have to speak. Okay, what could go wrong? Okay, you're shy. So what could go wrong? For example, think about it. It's the binding is dependent on the humidity. Okay, the humidity percentage in the system. So different humidities, and this is a problem because the humidity. I don't know what the humidity in Xi'an now, but the humidity in Ben Gurion is something like 20%, 30%. But if you use this device here, Ben Gurion, and use the device in Xi'an, you're going to get different results because the humidity. Another way is how do we introduce only the spores or the gas phase? So we need some kind of a way to have an inlet that pumps in the gas with the spores. What about interferences? Could be other molecules that will bind to the antibody in non-specific interactions and will affect our the thing that it measures, or even will bind not the antibody, the cantilever itself. There are some places on the cantilever that they don't have the antibodies, and in the air we have, I don't know, different types of other molecules, and they will bind to the cantilever non-specifically and will change the mass. And by accident, we can see some changes in the resonance, but that won't be because of the spores. That will be because of some interferences of molecules that are not related to the spores and bound to the cantilever and change the mass. Okay, any questions?
I want to ask if the sensor can respond after the test.
If the sensor can what?
Response.
Reuse?
Reuse, yes.
First, excellent question. And thank you very much for asking the questions. And very good. So the question is if the sensor can be reused. Okay, we took the sensor to some place, we measured the spores, we got some values, we monitor the spores. Okay, fantastic. Now let us say, does it a one-time use, or we can somehow clean it and reuse it? So it's an excellent question, and the answer is that yes, it can be reused. If you have antibodies that bind the spores from the first measurement, we can now use some materials that can dissociate the spore from the antibody and freeing all the antibodies. And then now we can, after we cleaned it, we can take the sensor to a new location and do the sensing again. Now, sorry, what?
Oh, I understand.
Great. And actually, it's very much used. This kind of method is used to reuse the sensor. But practically what's happening is that when you try and you remove the spores, you also remove a bit of the antibodies. You kind of ruin a bit the sensor. So what is very important is not putting new antibody, is that it is to see what happens to the background signal. Okay, this is the first part. When you have only with the antibodies, the measurement will start at a different frequency now because we have less antibodies now. But we're still going to get the changes that we expect to have. Great question. Any more questions? Okay. Thank you. Now, here we finish. I told you it's going to be a bit shorter class today. And we're going to try to summarize what we studied today. The first question is, what is the receptor here? What do you think? We have the cantilever, we have the antibody, we have the spore. Which part is the receptor? What do you think? Let's do like this. Whoever think that the receptor is the cantilever, raise their hands now. What is the name of the TA again? Sorry. TA? What's your name?
My name is Suchen.
Shuchen?
Yes.
Okay. Did anyone raise their hands for the receptor as a cantilever? You will count how many people? No? Okay. Thank you. You will be my eyes. Who thinks that the receptor is the spore? Raise their hands. Who thinks it's the spore, is the receptor?
There's nobody with.
There's what? Someone?
Nobody.
Nobody.
Yes.
Okay. Who thinks the receptor is the antibody? Raise their hands. Nope. Nobody also?
The receptor is antibody.
Who thinks the receptor is the antibody? Raise their hands. How many people we have, Shuchen?
We have 5, 6 students.
Six students. Okay. So you're right. The receptor is the antibody. Remember, receptor is the one that provides the selectivity to the analyte itself. Which one of the physicochemical reactions could be the limiting reactions? Okay, so you remember at the beginning of the class, we talked about the limiting reaction. And the first part is looking what kind of reactions we have. So we have diffusion of the spore towards the analyte, towards the antibody. We have the binding reaction. Okay. So there are two main processes, physicochemical reactions. And the question, what could be the limiting reaction? And here, the limiting reaction is basically usually it's the diffusion, is the mass transfer. This is what happens when it's very, very slow. And now the question is how you will improve the sensitivity of the lab on a chip. How you will make the sensor more sensitive. What do you think? Does anyone has any idea? How can we make the sensor more sensitive? Remember that? Remember that we said here in B that in a very low analyte, and now analyte is the spores, right? And the receptor is the antibody. So if we want to increase the sensitivity, we need to decrease R0. So what we actually need is we need lower R0, lower receptors. So if we will decrease the concentration of the receptor, we'll get a much more sensitive a sensor to Aspergillus niger. Okay, any questions on this slide, on the summary or any of the slides? Okay. So here finish unit number 4, which is miniaturization and physicochemical processes at the interface of the transducer. We wanted to recognize different types of receptors, such as enzymes or antibodies. We analyzed the mechanism that happens at the receptor's vicinity, such as receptor-analyte interactions. We saw the equations that describe the reaction kinetics or the concentration eventually of the complex of the analyte and the receptor, which is correlated to the concentration, to the signal that we measure. We also saw that how it can be used in applications such as the Aspergillus niger detection and how it affects the transducer behavior. Okay, tomorrow we will continue understanding what happens at the physicochemical transducer, or we're going to study about bioelectrochemistry and how basically you can use what are electrochemical transducers that translate the presence of the biochemical molecule into electrical signal.